Hi, I'm Eunice and welcome to my quick talk about the opportunity I had this past school year with NASA Langley Research Center, mentored by Dr. Cho Park and Dr. Sang-Hyun Chu. The project I worked on is called MOOSE, or Metal Matrix Composites for On-Orbit and On-Surface Services in Extreme Space Environments. The purpose of MOOSE is to explore the potential of boron nitride dispersed in a metal matrix. As a coating, it can be applied as a protective layer on many surfaces. As a bulk material, it may be used as trusses or other types of mechanical supports. With no atmosphere on the moon, the mechanisms sent for scientific exploration are exposed to high radiation levels and extreme temperatures. Additionally, the lunar dust and regolith are significantly abrasive, creating extensive damage to technology. As a reinforcement material, boron nitride nanotubes address these challenges and more. The first part of my internship was investigating potential processes to deposit the mousse coating. Thermal spray is a common method for coating application where the material is fed into a spray torch, then propelled onto a substrate. However, thermal spray encompasses a wide range of processes that use various levels of kinetic energy and thermal energy for deposition. Through a literature review, some common types of thermal spray were explored. Aerosol deposition and cold spray rely on kinetic energy to mechanically deform and bond particles. The particles are accelerated using convergent-divergent nozzle, which compresses, then expands the flow, causing particle acceleration. Cold spray is favorable since its exit velocity is very high, up to 1,000 meters per second. This high velocity results in such a high energy impact that a residual stress is created between particles. In this case, this stress is beneficial and increases the overall strength of the coating. On the other hand, plasma spray methods rely on thermal energy to melt the particles. Plasma gases are heated by the torch, then propelled, carrying the particles to the substrate in a high temperature plume. The material then cools and hardens into a dense, uniform coating. The environmental conditions during manufacturing play a significant role in the coating quality, as exposure to air causes oxidation of the materials, resulting in defects in the final coating. Therefore, spraying in a vacuum environment is optimal. High-velocity oxygen fuel uses a combination of kinetic energy and thermal energy. Like cold spray, this method uses a convergent-divergent nozzle, but its thermal energy is provided by combustion, which uses oxygen and fuel. This results in a supersonic particle velocity. However, the use of oxygen increases the risk of oxidation. Ultimately, cold spray and vacuum plasma spray were selected to be evaluated further through experimentation. The next issue I addressed is the feedstock, or the powder that is fed into the thermal spray torch. The flow into the torch is governed by the powder material properties. Ideally, the feedstock would be spherical and highly dense particles. It should also flow at a high feed rate and have low interparticle cohesion. Boron nitride nanotubes and nanopowders don't fit into this characterization. One way to solve this is through cryogenic ball milling prior to spray deposition. Ball milling is used to tune the morphology, size, and dispersion of powder mixtures. At cryogenic temperatures, the powders become brittle and the milling process becomes more efficient. Besides spherical particles and nominal size distribution, the boron nitride should evenly coat and bond to the surface of the metal particle to ensure even distribution of the boron nitride in the final composite coating. The process variables that influence the quality of the final powder, such as potential additives, ball size, rotation speed, milling time, just to name a few, are still being investigated through both literature review and experimentation. Boron nitride nanotube reinforced metal matrix composites are an exciting alternative to current materials used for space exploration technology. As a coating, it can be applied to a variety of shapes and sizes via plasma or cold spray. To ensure high-quality coatings, cryogenic milling is being investigated to optimize the feedstock used for these specific manufacturing methods. Thank you for listening to my presentation of the work I completed for the MOOSE project. A special thank you to the North Carolina Space Grant, the Advanced Materials and Processing Branch at NASA Langley, and my mentors, Dr. Park and Dr. Chu, for allowing me this opportunity to participate in the exciting field of space exploration materials.